Now, our work with finite sets may seem to be a bit much. Okay, we all know how to count, but that rigor will inform what we want to do with infinite sets. Recall, we have non-empty sets x and y. We say that x and y have the same cardinality if and only if there exists a 1-1 correspondence f that carries x to y. So here we're going to take all the points of x and we'll use f to give each point a y label. So we're just relabeling the points. We've seen if x and y are finite, this just means they have the same number of elements. Now, we want to talk about infinite sets here. So definition. We'll say a set x is infinite if and only if it is not finite. From last time, we saw this is equivalent to saying there exists a 1-1 correspondence between x and a proper subset of x. So for finite sets, okay, if I try to fit a finite set into itself, the fit is perfect and there's no room left over. With infinite sets, we can fit them inside of themselves and we have room to work in. Now you might think this is the end of the story. Okay, we have finite sets, then we have infinite, but there are going to be many different types of infinite sets. First type that we consider, the natural numbers. So here, okay, we have 1, 2, 3, and so on. I could set up a 1-1 correspondence between the natural numbers and a proper subset just by setting each n to n plus 1. So this set is infinite. Now, this set's special enough that we have a definition. A set x is called countably infinite if and only if there exists a 1-1 correspondence f that carries the natural numbers to x. If this occurs, okay, the notation is cardinality of the natural numbers. We say as aleph null. Now what does this mean? So why countably infinite? Well, what we're doing here, to each point in x, we're going to assign a natural number. So this is the same as just putting all of our numbers, okay, all of our points in a list. So we have x1, x2, x3, and so on. At every point we can put a natural number to. So that's what we mean by countably infinite. The set's infinite, but we could tag each point in the set with a natural number. Now, this picture here is going to be useful for visualizing some of the arguments that we use. Now, let's look at the different ways to make room in a countably infinite set. Here we're going to work informally. So recall the game is just to label each point with a natural number. So first, if I take a finite set union with a countably infinite set, we get a countably infinite set. The trick here is to shift. So if we have our labels, okay, I want to fit these 3 points into this sequence. What can I do? Well, if y is a countably infinite sequence, I just shift everything over by 3, and then I have room to put our first 3 points. Then everything gets a label from the natural numbers. If I want to take countably infinite set, union with a countably infinite set, to get something that's countably infinite, we splice. So the idea here, okay, we're going to have a set of x's, okay, labeled by the natural numbers, a set of y's labeled by the natural numbers. Then we're just going to alternate. So I'll do x1, y1, x2, y2, x3, y3, and we see that that's going to give us a natural number for each element in both of our sets. So we take the union, countably infinite. A little bit more complicated. Okay, so this is going to be like a splice, only the pattern is going to be a little bit different. So if I take the countably infinite union of countably infinite sets, okay, we get, again, countably infinite. We want to get everything labeled with a natural number, so what do we do? Okay, I'm going to have a countably infinite union of these sets. So that means, okay, we'll have our first sequence of points here, second sequence, third sequence, and note, all these sequences of points, I can give an index by a natural number. So then what do we do? Well, the idea is I want to pick off every element that shows up in this grid. So we just do the pattern as follows. Okay, so we start up in one corner, go out by 1, and just keep zigzagging back and forth. Now that's going to exhaust every point on the grid. So every point is going to get a natural number as a label. And then if we want to write it out as a sequence, Okay, well, we could start doing that, but to give it a general formula, it's going to be a little bit difficult. We just need to know that we can do it. For a concrete example, the integers form a countably infinite set. First, we could list the integers as a sequence indexed by the natural numbers. So 0, 1, minus 1, 2, minus 2, and so on. For an explicit 1-1 correspondence, we'll have f carrying the natural numbers to the integers, sends n to 1 minus n over 2 if n is odd, n over 2 if n is even. They'll leave it to you to show it's a 1-1 correspondence. In fact, it's just going to generate the sequence we have here. Next, definition. A non-empty set X is called countable if and only if X is finite or countably infinite. So the idea here, if I want to get control of a set, if it's countable, then we get control by labeling every element with a natural number. So all the numbers are accounted for by placing numbers on them. Now, if we're not countable, this means, okay, if we label using the natural numbers, no matter how we do it, there are always going to be points left over. So it can never capture everything using the natural numbers. I'll say more about that in a little bit. For now, we want to develop properties of countable sets. So first, okay, we have theorem. It's going to be the analog. Okay, the statement for finite sets would be, if a set has n elements, then every subset has less than or equal to n elements. So every non-empty subset, B, of the natural numbers is countable. For the proof, okay, if B is finite, then there's nothing to show, we're done. Okay, finite implies countable. If B is not finite, we want to invoke the well-ordering principle for the natural numbers. So this says, if we have a non-empty subset B of the natural numbers, there exists a smallest element, B1, in B. We're going to apply the well-ordering principle repeatedly to generate a sequence of natural numbers. Okay, so for instance, if I start with B, we're going to have a smallest element, B1, so it's going to be the first element in our list. Then we're going to throw away B1 from B and repeat. So that'll give me a B2. Then we throw away B1 and B2, we get a B3, and so on. So we get a list. Now, if it terminates, then that means our set's finite, and that's going to be a contradiction. So what we have to ask is, when I generate this list, do we get every element in the set B? Well, if I miss some m that's in B, okay, how do we get to m? I start at 1 and apply the successor function m minus 1 times. So we can apply the predecessor function m minus 1 times to get back to 1. If I missed this m, so that means m was never the smallest element in some subset when we do all these throwaways, that'll mean that all of our b's are going to be strictly less than m. So that means we have all of these elements contained in 1 through m, and that means the b's are going to form a finite set. That's going to contradict our assumption. So that means every subset of the natural numbers, okay, non-empty, is either finite or countable. If we include finite sets, we can rephrase our previous result as every non-empty subset of a countable set is countable. This leads to the following theorem, which extends our result for finite sets. So if B is non-empty, the following are equivalent. First, there exists an onto map F from the natural numbers to B. Second, there exists a 1-to-1 G carrying B to the natural numbers. And finally, 3, B is countable. For the proof, it's exactly the same as in the finite case, so I'll refer you to the previous video. Now, this allows us to work with onto and 1-to-1 maps instead of 1-to-1 correspondences. So for example, if you consider our grid argument from before, okay, we use that to show countably infinite union of countably infinite sets is countably infinite. Okay, and there, the argument would work with disjoint sets. We can remove the disjoint property. So we'll be allowed to double count. Instead of having a 1-to-1 correspondence with the natural numbers, we'll have an onto map from the natural numbers to our list. Now, rephrase that as corollary. X is non-empty. we'll have a family of subsets, A sub I, indexed by the natural numbers, each countable. Then the union as I goes from 1 to infinity of the A sub i's is a countable set. Example, okay, we take the rational numbers. We can write this as a countable union. So we're going to take I going from 1 to infinity. We'll take a set of integers, and then we're just going to divide each integer by I. So we're going to take all of these sets, take their union, and that's going to cover all of our rational numbers. Okay, and the rational numbers are going to appear in many of these sets. So this set is countable. It'll be countably infinite because it has the integers as a subset. So if it were finite, then every subset would be finite. So this has to be countably infinite. Another corollary. Okay, we have finite Cartesian product of countable sets x sub I will also be countable. Now, for an example of this, let's consider the product of the natural numbers with themselves. I can write this as a countable union of countable sets. So these countable sets are just going to be the sets, we'll take singleton I cross with the natural numbers. So each of these is just going to be the set of ordered pairs, I comma n, where n ranges over all natural numbers. So countably infinite. So we have a countable union of countably infinite sets, so this set is countable. That leads to the question, can a countably infinite product of countable sets be countable? The answer in general is no. This is going to give us examples of uncountable sets. Now, our main technique is what we call Cantor Diagonalization. For an example of a countably infinite product that's not countable, I'm going to use a set of all binary sequences. So this is going to be the countably infinite product of the set 0, 1 with itself. So here I just take any sequences that consist of zeros and ones. Now, what this says, if we try to attach labels to each of these sequences from the natural numbers, there's always going to be some left over. The natural numbers is not enough to get control over all of these. Theorem, there exists no one-to-one correspondence F from the natural numbers to our set B. For the proof, proof by contradiction, we'll assume that we have a one-to-one correspondence. So that means for each binary sequence, we can attach a natural number. So these are going to occur in a list indexed by the natural numbers. I want to show that I can produce a sequence that doesn't appear in this list. Since our one-to-one correspondence is arbitrary, that shows that no one-to-one correspondence can capture all the binary sequences from the natural numbers. What do? We run down the diagonal. So I'm going to construct a new element by just comparing diagonal entries. So for our first element, we take a look at A1. If that's a 0, our first element here is a 1. If it's a 1, our first element here is a 0. And no matter what happens with the remaining entries, there's no way this element is equal to our first element. For the second entry, we look at the second element in the list. We look at the next element on the diagonal, B2. If it's a 0, we have a 1 here. If we have a 1, we put a 0 here. No matter what happens otherwise in the sequence, this element will not be equal to the second element in the list, and so on. Now, as I run down the diagonal, I'm going to pick off entries that differ from the entries of each of these on the diagonal in the right spot. So this element will be equal to none of the elements in our list. I've produced an element that's not in the list. So contradiction. First corollary, the power set of the natural numbers is uncountable. In fact, cardinality of this set is the same as the cardinality of the set of all binary sequences. Now, to show this, to each subset of the natural numbers, which is not empty, we'll assign a binary sequence. And we'll do so in a way that's one-to-one and onto. So for each subset of the natural numbers, not empty, we have our list, 1, 2, 3, 4, and so on. If 1 appears in the subset, we give it a 1 in its entry, otherwise we give it a 0. And then likewise for all the other entries. So for instance, 2, 3, 7 we'll have a 1 in the second, third, and seventh spots, 0 elsewhere. For the evens, okay, well, for 1 we have a 0, for 2 we have a 1, 3 we have a 0, so we're just going to alternate between 0s and 1s. For the set of all natural numbers, with remainder 2 upon division by 3, okay, I'll start with a 0, then we have a 1 for 2, I'll have 2 zeros, then a 1, 2 zeros, and a 1, and so on. So this assignment is going to be a one-to-one correspondence, so these two sets have the same cardinality, so uncountable. Next corollary, okay, this is a big one. The interval from 0 to 1, including 0, is uncountable. So we have a subset of the real numbers which is uncountable. That means the real numbers themselves are uncountable. For this, we're going to use the same diagonalization argument, and we're just going to modify it a little bit. So for each decimal, okay, that's in between 0 and 1, okay, so these are just decimals with no integer part, we have a sequence, and we're just going to assign that to a sequence of numbers between 0 and 9. Now, we can set up the same diagonalization argument. Instead of switching between 0s and 1s, we have a lot more freedom. One thing we want to be careful about is when we do our switches, to not switch to 0 or 9. So a problem we have with using this decimal representation is that it's not unique. So the famous problem that goes with this is whether 1 is equal to 0.999 going on forever. So these two numbers are going to be equal, okay, if we go by the definition. So I'll do that on the next board. By not switching to a 0 or 9 ever, I don't have to worry about this business of having a number represented in two different ways and accidentally appearing on our list in a different form. Just in case, why does 1 equal 0.9 repeating? There are two ways we can go with this. If we don't want to bother with a definition, we just want to believe it. Okay, we have that 1/3 plus 1/3 plus 1/3 equals 1. In decimal representation, we have that 1/3 is 0.3 repeating. So if I add that to itself 3 times, we're going to get 0.9 repeating. So these have to be the same. If we go to the definitions, okay, well, what does it mean to be a decimal between 0 and 1? So what is point A1, A2, A3, and so on? Here, this is just a series. I'm taking A1 over 10 plus A2 over 10 squared plus A3 over 10 cubed, and so on. That means 0.9 repeating is 9/10 plus 9 over 10 squared plus 9 over 10 cubed, and so on. So I have a geometric series here. Now, if I want to sum a convergent geometric series, okay, I want a 1 in the first spot, so I'll factor out a 9/10. When I do that, we'll see that we're taking 1 plus 1/10 plus 1/10 squared, and so on. So our r is equal to 1/10. The absolute value of r is strictly less than 1, so our series converges, and we can take its sum. For the sum, we're going to have 9/10 times 1 over 1 minus 1/10. Okay, so this is going to be 1 over 9/10, and so that's going to cancel to give us a 1. So 0.999 is equal to 1 using our definition using series. Now, because the interval from 0 to 1 is uncountable, okay, if R, the real numbers, was a countable set, every subset would be countable, but we know that's not the case. So the reals are uncountable. Corollary, that means the irrational numbers are uncountable also. If they were countable, okay, well, the reals is equal to the union of the rationals and irrationals. So if this was countable and this was countable, then their union would be countable, but we now know that R is not countable, so that means the irrationals are uncountable. Now, some final notes. First, we want to take a look at some fallacies using arguments with Cantor diagonalization. So these are just ways to use Cantor diagonalization in the wrong way. First thing we could try to show, that the natural numbers are uncountable. Okay, so that statement really doesn't make sense off the bat, but let's just see how the argument would go that you would try. Well, we're going to set up a list. Okay, now this list isn't going to go to the right. Okay, entries are going to go to the left. So we'll set up a list of natural numbers. Then we're going to take a diagonal, try to create a natural number that's not on the list. Now, an argument like this won't work because for every natural number, okay, it's going to only come out to a finite number of spots going this way. So this is going to create a sequence of natural numbers that's infinite, which is not going to correspond in general to another natural number. So an argument like this is going to be, okay, not correct. Another bad argument. The statement is, the rational numbers form an uncountable set. We know this is false because we proved that they were countably infinite. If we set up our argument, okay, here we'll just show it for rationals between 0 and 1. So each of those rationals, we assign a natural number, we form a list. Then we can go down the diagonal, construct a sequence which is not in our list. Now, to get a contradiction, I would need to guarantee whenever we do this, we always get a rational number back. Because we know that the rationals are countably infinite, in this list we'll have everything. So what we produce when we go down this diagonal would have to be an irrational number. So we're not going to get the contradiction that we're looking for. Finally, we note some further results, but we don't go into them in any depth. So first, we have the Schroeder-Bernstein theorem. This is going to say if F is a mapping carrying A to B, which is 1 to 1, we have a mapping G from B to A, which is 1 to 1, and the cardinality of A is equal to the cardinality of B. So here we have a test for cardinality without actually constructing the 1-to-1 correspondence. Next, we have the statement that if I take any non-empty set X, its cardinality is going to be strictly less than the cardinality of its power set. Now, what do we mean by this here? This says that we have a 1-to-1 map F carrying our set to its power set, but we don't have a 1-to-1 correspondence between the two. Okay, so by Schroeder-Bernstein, that says there's no 1-to-1 map from the power set back to the set. What makes this interesting? Okay, what cardinalities do we have so far? We have all the finite cardinalities. We have the cardinality of the natural numbers. We have the cardinality of the binary sequences. And this gives us a way to create a whole tier of uncountable cardinalities by taking power sets. If we take a step back, we have the Continuum Hypothesis. So what this asks, are there any cardinalities between that of the natural numbers and the real numbers? Okay, and so the hypothesis is that there are none. This leads to some interesting results in logic.